In this problem, we are going to solve a perfectly inelastic collision. Now, you might ask, how do I know whether it is an inelastic, perfectly inelastic, elastic collision? Well, if you're told in the problem that the objects become one mass after the collision, then you know it's a perfectly inelastic collision. One hallmark of a perfectly inelastic collision is that the objects smush together after the collision and then become one combined mass. Another way you can tell the difference between an elastic and inelastic, if the problem doesn't tell you, is that you can think about finding the kinetic energy before and after the collision. If the kinetic energy before and after the collision are the same, you have an elastic collision. If the kinetic energies, total kinetic energies of your system before and after the collision are not the same, then you have an inelastic collision. So here, a clay ball of mass, let's say that's mass 1, 0.24 kilograms, is moving to the right at a velocity of 1.32 meters per second. I'm going to call that V sub I initial, the velocity initially of my first ball of clay. A second clay ball of mass 0.45 kilograms is moving to the left at 1.32 meters per second. It's moving to the left. I'm going to give it a velocity of minus 1.32 meters per second. If we're going to call to the right positive velocity, we're going to call to the left a negative velocity. So the magnitudes of their velocities are the same, but they're moving toward each other. So one of those velocities needs to be positive, the other one needs to be negative. The balls have a perfectly inelastic collision. This is what our system looks like before the collision. Here my collision happens. This is what my system looks like after the collision. Perfectly inelastic collisions means that both of those masses are going to combine, and then they're going to move off in some new direction with some new velocity. What is the final velocity of the combined mass? And that's what we're going to solve for. So this is perfectly inelastic. In all collisions, the momentum is conserved. The kinetic energy is not going to be conserved here. But in order to find the final velocity of my combined mass, all I have to do is use conservation of momentum. So the sum of the initial momentum of my system has to equal the sum of the final momentum of my system. So the initial momentum of mass 1 would be m1 v1 initial, plus the initial momentum of my second ball will be m2 v2 initial. And that has to equal the momentum after the collision of my combined masses. So those masses are going to smush together and become one object, and they're going to move as one object. So now the mass times the velocity, that mass is going to be the sum of both of their masses, because they have smushed together to become one new object, times the final velocity after the collision of this new mass. So all we have to do now is solve for V final here. So I divide both sides by m1 plus m2. It cancels those here. Divide by m1 plus m2. So V final, I'm going to put that out in front of my equal sign, equals m1 v1 initial plus m2 v2 initial all over m1 plus m2. So now, let me move over here so I have more room. I'm going to put in those numbers. So the mass of my first clay ball was 0.24 kilograms times its velocity was 1.32 meters per second plus the mass. Actually, let's just tidy this up here. m1 plus m2. Plus the mass of my second ball, which is 0.45 kilograms, times the velocity of my second ball before the collision, which was minus 1.32 meters per second. I have to keep that minus sign on here. Remember that momentum is a vector, these velocities are vectors. So if they're moving, those objects are moving toward each other, one of those velocities has to be positive, the other velocity has to be negative. So I've got m2, v2 initial here, and I'm going to divide it by the sum of the masses, m1 plus m2. So 0.24 kilograms plus 0.45 kilograms. All right, and then that will equal, on top, if I do just this top row, or the sum of these quantities above, on the top of my fraction, that's going to be minus 0.2772 meters per, kilograms times meter per second. Say kilogram meter over second, because we're taking a mass and multiplying it by a speed. And then we're going to divide that by the sum of these two masses, which is going to be 0.69 kilograms. So I have minus 0.2772 divided by 0.69. I see that the units of kilograms cancel on top and the bottom. So I'm just left with units of meters per second here. And my answer is going to be negative. So my final velocity for the combined masses after the collision is going to be minus 0.402 meters per second. So after the collision, okay, these two masses collide, and then the combined masses actually is going to move off still to the negative direction. This is our direction for V final. So why does this mass move in the negative direction? Well, let's think about our initial conditions here. We have both of our clay balls have the same magnitude of the velocity, so they have the same speed and they're coming in toward each other. But mass 2 has the larger mass than mass 1. So mass 2 is coming in already with a greater momentum than mass 1. So when they're combining, and if we're conserving momentum, that means that the combination of those masses after the collision is going to continue on moving in the same direction as my clay ball with the larger mass.